Hello, my name is Sam Black. Today I'll be presenting our work, Visualizing Paired Image Similarity in Transformer Networks, co-authored with Abby Stilianu, Robert Pless, and Richard Souvenir. In the field of deep learning, interpretability algorithms aim to explain why models make the predictions that they make. For computer vision models, oftentimes these algorithms produce a heat map that highlights the relevant pixels from the input image. The choice of the algorithm is predicated on the model architecture and the prediction task. Here, this example demonstrates a heat map of the most important pixels for this cat picture that is inputted into a CNN and trained for classification. For models that are trained for image retrieval, it is useful to know the regions from a pair of images that the model encoded to be similar to each other. These visualizations are known as paired similarity maps. Stiliano et al. Introduced a paired image similarity visualization method for images encoded with a CNN. In this work, we introduce a similar method, except for images that are encoded with a transformer. For CNNs, many explainability algorithms take as input the intermediate feature maps that are generated by the network. Due to the local support of the convolution and pooling operations, the source of information in each spatial feature can be directly mapped back to the corresponding location in the input image, which allows for generating intuitive visualizations. This is illustrated in the example here on the left. For image transformers, the global attention operations mean that the source of information from a given spatial feature can be traced back to theoretically anywhere in the input image, as shown here on the right. This makes generating intuitive visualizations challenging. In transformers, the attention weights at each layer quantify the amount of information exchanged between tokens. Modeling the attention flow throughout the network can provide insight into the inner workings of the model and help determine the most relevant components of the input sequence. One method for approximating the attention flow is rollout, which iteratively multiplies the attention weights at each layer to generate a linear approximation of the source of information in each output token from the input tokens. This brings us to our three-step paired image visualization method. First, each image is processed through an image transformer, and the output tokens are pulled together to generate the global image feature embedding. We utilize Stiliano et al.'s method to spatially decompose the similarity back to the output tokens. This step involves multiplying the complementing image's global feature embedding with each output token prior to the pooling layer to generate a pre-distributed similarity map. Second, we approximate the attention flow throughout the network to generate the attention distribution matrix. While any attention flow approximation method would theoretically work, we use rollout. Finally, we multiply the attention distribution matrix with the pre-distributed similarity map to redistribute its mass to the input tokens. The result can be upsampled and overlaid with the input image to generate an intuitive visualization that highlights the most similar regions between each image according to the model. For our primary evaluation, our image transformer is a pre-trained VIT base model that we fine-tuned on 3 image retrieval datasets: Hotels 50K, Google Landmarks version 2, and Stanford Online Products. In these examples, you can see that only the most relevant areas of each image pair are highlighted with bright red, which indicates the highest level of similarity. We can also see how the image similarity maps converge over the course of training. Pictured here are 2 example queries and their top 3 matches, with a green border indicating a correct retrieval. The similarity maps of the retrieved images converge from being spread out all over the image at the beginning of training to only highlighting the regions that are visually similar with the query by the end. We can also generate output agnostic visualizations and compare them to the similarity maps to see how they differ. To do this, we sum the rollout attention distribution matrix to generate an output agnostic rollout map to see the most attended to tokens. When comparing these with the similarity maps generated with respect to the complementing image, only the common features of both images are highlighted. Lastly, we also train a comparably sized ResNet 101 on these 3 datasets for comparison. We find that both models achieve similar aggregate performance. However, the sets of retrieved images for a given query often differ between the 2 models. We find that VIT often retrieves images that have similar objects as the query, while ResNet matches are more dependent on texture. In this example, the VIT retrievals all share a similar set of furniture items as the query, including a television and dresser. The ResNet retrievals are matched on the carpet, as shown here by the similarity maps. For the Hotels 50K dataset, we quantitatively measure the similarity in perspective using pose similarity, which measures the similarity of 2 images segmentation maps. We find that VIT retrievals have greater pose similarity with the query image compared to ResNet, which reinforces the notion of VIT's object-focused retrieval approach and a greater degree of overlap in the retrieved image's perspective. This concludes the presentation. Thanks so much, and come check out our poster to learn more.